Okay, Dave,
Yes.
let's mute again and then start up the recording.
All right.
Okay, again, I want to give my warmest welcome to everyone who's joining us here tonight from Chapter 21 and those chapters outside of Chapter 21 as well. And for tonight, we're going to talk about Telechron ship's bell clocks. And this is primarily focused on repair and restoration tips. So one of the things that I discovered in the process of restoring these clocks over the years is they can be absolutely the most confusing things if you've never seen one before. I was quite daunted the first time I ran across one of these things. And it took me quite some time to kind of work through it. But once I did, I realized that they're not at all difficult. It's just that you got to know the tricks. So having accumulated the tricks, I thought I'd use this as an opportunity to share them with others who I know have also had similar frustrations with these things, especially if they're not regular electric clock repair folks. So this is what we're going to cover. We're going to talk about the movement restoration, and primarily what we're going to hear a lot about is getting the strike sequence correct on these things, getting it to work. We're not going to cover the rotor. At the end of the presentation, I have references for places you can go to get rotors restored or repaired or just plain replaced. I also wrote a series of articles a few years back. I can't remember when it was now. I think it was 2018 on the Telechron rotor and how to restore it if anyone wanted to look that up and take a shot at doing that themselves. It turns out, too, that it's not just the ship's bell. Telechron made a number of striking movements, hourly striking movements, hour, half hour, that are based on the same principles that were used in the design and the development of this movement. So pretty much every repair issue and problem that we're going to talk about resolving related to the ship's bell also applies equally well to the striking movements. And not all striking movements that Telechron made, but quite a few. So the little bit of the inspiration for this presentation. So this is what happened. I ended up getting, if you look down at the bottom right here, the Resolute Model 6B17. I ended up getting 2 of those clocks in for repair, 2 different customers, but absolutely identical clocks in every way. Not totally the same color case, but very similar finishes. So, and I was working my way through those, and I thought, well, I wonder if other people have been working on these clocks. Did a little bit of Googling and found a number of the statements that are listed here, some of which are on the NAWCC post. Here's some quotes. This movement was a Telechron embarrassment. They're not worth repairing. They can't be repaired. I would have to spend days on it. Just shut off the bell, replace it with a quartz. Well, I can understand their feelings. I truly can. What I experienced with these things is that, having worked on a few over the years, I now realize that they are unconventional and they are unfamiliar and they can be confusing, but when you really look at the thing, they're quite innovative too. Most of the problems with these things boil down to a couple issues. They're often set up wrong. Telechron actually made it easy to set these clocks up, but not if you don't know what to do. So, and one of the problems these things have is there is no literature that I have ever found on how to service these things. Now, I know it's out there. I just have not found it. So we had to invest in the time to develop all the methods over the years in order to figure these things out. A lot of these things end up being tinkered with for obvious reasons. There's a lot of fiddling that goes on when you don't understand why something doesn't work. And in general, most of the wear elements in these things are fatal. The things that are, when they wear, they go out, and then there's no way to get them to work right unless you correct the issues with the wear in these clocks. And just while I'm on this slide, I also want to point out that some of these clocks are rather handsome. These two Resolutes that I have are just gorgeous clocks. The finishes on them are still in good shape. I literally cleaned one of the cases with a damp cloth, and it looks like it was polished to a high gloss. It is unbelievable. It looked completely dull when it came in, and just a damp cloth cleaned it up. So they tend to hold up pretty well. The cases do. I mean, you know, the usual things, if you leave them in heat or sunlight, things like that, they'll tend to get a little bit weathered. But so now Jim Lentz is a really good reference. If you want to look at or learn about the array of Telechron clocks that were produced between the 30s and the 60s, there are tons of them. And Jim Lentz does a really good job of pulling all of those models together, a good number of them anyway. I was able to find the 4 major models of the ship's bell clock, and you can see the 2 of them here. 2 of them were on the previous page, as we showed here, the Yachtsman and the Resolute. And here we have the Gloucester and the Nantucket. And they all are unique in some way, and they're all basically the same movement throughout all these things. And you can usually tell you got a ship's bell when you see the little, you know, steering wheel kind of effect that's done with the woodwork around the dial with the little finials there. So when you see that, you're probably dealing with a Telechron ship's bell. Now, there's also a version of that style that's built into a much smaller case that's called a Telechron ship's wheel. And that is not the same. It's usually a time only, sometimes time and alarm, but does not have the strike feature. And here we got we list out the various model numbers and the years during which they were produced. And again, we have at the end of this program the reference list for this book and the information if you want to order the book. I believe it's still in production. Oops. Okay. So it is a rather unusual movement, as you'll see as we go through this thing. One of the fascinating things about it is there's very few parts in this thing. And it is a basic time train with seconds hands and a couple of parts added to make it strike. And as if you look at it long enough, you'll realize it's not too hard to visualize once you kind of get past the demystification stage. The funny thing about it is there are several different versions of a strike movement and chime movement that Telechron built. And most of them are huge loads on the motor / rotor when they drive the strike sequence. This one actually gets power back from the strike mechanism when it's striking. It actually pushes on the rotor to make it move forward. So it literally does not load the motor to run the strike. And in that regard, it's quite unconventional. So if we were to go and take the top plate off, we're looking dial side into this thing. This is what's there. And as you can see, I mean, one point that comes across pretty quickly is there's not much here. Now, I did remove the hour wheel that also has the snail for the strike sequence. That's removed. We'll show you that part in a little bit here, but this is what happens when you just take that one hour wheel off. You can see everything pretty clearly. Down here, you see the flag, which tells you whether the power was lost at some point. This is called this is the strike rack here, the large metallic steel rack. That is what makes this thing strike, and it drives the strike. You can see the spring down here. You load that spring when you assemble the clock, and it drives the strike sequence. And it's what lifts, it literally is what transfers the power to lift the hammer to strike the bells. So, and the number of strikes is determined by obviously clearly the snail, and then the other thing is where the strike pawl is when it drops off of the cam. And the minute cam, you can see it here. It's this sort of funny shaped little thing, this S-shaped thing that comes all the way around to the other side over here and goes underneath the rack on this side. So it's a fairly large ordeal. And the reason is because there's a roller here that is used to, it's actually what drives, it's where the pressure is applied by the minute cam to lift that rack and wind it into position so that it's armed and ready when the pawl falls off the edge of the cam when it's time to strike. So it's this whole strike sequence starts by this rack being wound, being loaded during the forward movement of the minute cam and released to turn the strike wheel during the strike sequence itself. Now, the strike wheel is by way of a ratchet geared to the rotor of all things. And that's what controls the speed at which it strikes. Now, you can imagine without that, the rack would just jam this thing straight down and you'd get all your bells in about 10 milliseconds, boom, just like that. And actually, that's one of the symptoms that strike wheel ratchet has failed. And we'll talk a lot more about that here in a few minutes. But you can also see that on the left here, the strike pawl and hammer, I point to that. That pawl is concentric with the shaft that the hammer rides on. And it can be moved in either direction. And when it's moved forward and the edge of that, where the spring is coming out here, where that touches the hammer, the arm for the hammer, it pushes that arm out of the way and drops it and allows it to strike. So that moves both ways. That way this rack can actually wind, if you will, the sequence and get it armed and ready to fire. And then the rest of these wheels are basically, minute wheels, intermediate wheels, idler wheels. We'll see when we take this thing apart in a few seconds here. Time set, and that's it. There's not much more to this thing. So if we remove the top level of wheels that we just talked about, what we're going to see here is there's a hole here where the rotor comes through, and there's a pinion on the rotor that drives this second wheel at about 1 RPM. And then that drives the strike wheel and the ratchet on that strike wheel keeps it moving. It's constantly moving and it's in the ready so that when that strike rack drops, it will immediately start back turning the rotor, if you will, or forward turning and more appropriately. And that which provides the governing for the speed at which it strikes. So, and you can see here the second's intermediate wheel, and there's a second hand shaft there that's also driven by the rotor directly. In fact, the only thing that second hand arbor does is ride the minute hand, the second hand. That's it. It does nothing else. It drives nothing else. So as a result, you rarely see any wear associated with that arbor or with what is associated hole. And then there's this thing we're going to talk a little bit about called the alignment hole, and we'll get to that here next. So let's move along. Whoops. I think I lost something here. Sorry. Let's get back to screen share. Okay, so, all right, so let's move on here. This is the strike wheel. Now, remember, we just talked about this wheel. This is the teeth of the strike wheel actually lift the hammer and drop it. The ratchet and pinion we talked about, this is a really important component. This is being turned basically clockwise in this photo. Constantly. It's always moving clockwise. And as a result, these clicks on each side are toggling as the tooth moves from one to the next and it keeps it in a position so that if the force from the rack comes and pushes this thing in the opposite direction, it grabs and drives the rotor and keeps the thing regulated in speed. So you can understand how important this function is. If you lose this, if this ratchet gets worn out or one of these clicks comes loose or something like that, you will have no way to control the speed at which this thing strikes. Or worse yet, you will have just enough grab to keep it from being a catastrophic fail and you'll lose a number of the strikes as a result of that. So the shift bell sequence will be greatly disrupted if this ratchet wheel is worn, or if these, in some way, these clicks or click rivets are damaged. Now, there's another thing I want to point to here, because it's very important, is that what I call the home detent. This little half moon cutout here is critical in setting these things up to be able to strike properly. And it's not a difficult thing, but I want to point it out now, because when we get to it later, I want you to not be surprised by, what are you talking about? Where is that you're pointing to, and so forth. It is right on this wheel. This helps set up the location of this assembly, where this thing is resting at the time that the cam is at the very top, ready to drop off and start a strike sequence. The location of that detent is going to be critical, and it's not difficult to set it, but you just got to know that you have to set it. Well, there's another interesting Telechron alignment trick. If you look at most of the Telechron striking and chiming movements, sooner or later, you'll see that there's a series of holes somewhere in and in the midst the striking components of that movement. And Telechron didn't put those there, for any other reason except to provide a convenient way for the service person, and probably the initial assembler and the manufacturer of the clocks, to set up the relative location of these various wheels. And as you know, if you have a cam that you need to drop off, and you have a snail that has to align at a certain point, it's either you're going to sit there and trial and error the thing to death, or you're going to have this trick that helps you kind of figure out what to do. And it's a lot easier to deal with setting this up in this case, I just use a number 42 drill, and you'll see that it passes through the hour wheel snail, the minute wheel cam, which you can see there. You can't see the hour wheel snail in this, but it does pass through it. It passes through the intermediate wheel, through the minute wheel, right down into the lower support plate. And if you run that 42 drill through there, you will have set up everything in this movement for the strike sequence, except for the final adjustment on that strike wheel that we just talked about. So that'll be all you have to do, is to set up that strike wheel, and you will have this thing fully aligned and working properly. So let's go through a quick disassembly of this thing and see if we can get this clock working. Again, as I said, this presentation was put together as a result of two of these clocks that were worked on pretty simultaneously. And you may notice some difference in the photos, but not substantially, because these two movements are almost identical in every way. And so, I could go back and forth between an assembled movement and a disassembled movement to put together the slides for this. It kind of worked out nice having two movements, but it also is a great way to prove out that this methodology does work, because it worked 2 for 2 on this set of movements. So what we're going to do here is first we're going to remove the bell, field and assembly, and the rotor. And those are located here. You can see the screwdriver here taking the two screws. The screw here on the left and the screw here on the right are what takes the field coil assembly and the rotor out. And it's just a simple matter of weaving it around the hammer and the adjustment, the time set arbor, and out it comes, and you can see it there. It's a few seconds later, you're taking apart, you're removing the bezel by unbending the tabs on the bezel. This is a little frustrating sometimes, because you don't want to have to take these apart too many times, because otherwise the tabs start to break off on these things. So, that's something to kind of keep in mind. Both of these movements didn't appear that there was a whole lot of effort in the past to take these bezels off. So that was good. As I will have definitely no trouble getting those tabs bent back and that bezel back in place again. Once you have the bezel and the glass off, then you can remove the hands and dial. Put the hands and dial in a safe place. I like to put mine in plastic bags, little baggies. It tends to keep them from getting scratched up. The bezel goes in the baggie. The glass goes in another baggie, so that they're all separated from each other and safe from mishap and set aside in another place so that they don't get, you know, anything, tools dropped on them or other parts dropped on them or whatever it might be. Then you take the 4 screws from that top plate, that there's a top plate right underneath this dial, and you take those 4 screws off and poof, there you are. That's what you see. And there's our little alignment hole there. So that's what's left. So then you come, okay, I'm going to take the rest of these parts out. So you take the major large components out. They lift right out. There's nothing to it. And then you need to remove the idler wheels. Now, these idler wheels aren't meant to be taken out, but they're not difficult to take out. You just need to remove the retaining washers that are kind of staked onto these arbors. And actually, it's the arbor itself that's a little bit staked over the washer, and prying with a screwdriver underneath the washer, a thin screwdriver, such as a watchmaker screwdriver that you can see there, will allow that washer to come free. And it gets a little deformed in the process, but you can easily flatten it back out with a hammer and a brass block, and you're in business for when you go to put this back together again. So on the right, you see all the parts. This is everything in this movement, 100%, nothing else there. That's it. Not very many parts. That's one of the amazing things about this movement, is how much they were able to do with so few parts. So for cleaning, we find that ammoniated cleaner is fine for pretty much everything. The one exception is the flag that lets you know that the power failed, with the red and white stripe on it that we showed earlier. Do not put that in the ammoniating cleaner. What I do is I'll dip it for a minute maybe in the Zenith 77 or just naphtha, and just brush it off and get the loose dirt off of it. And that's about as good as you need to do. Other than that, all the other movement parts are fine in ammoniated. You're going to probably have to use a brass brush, because these things get gummed up from nobody wanting to work on them. And that oil and dried varnishy dirt can be a dog to get off. So, and it baked on from the little bit of temperature rise from the rotor and the field coil and the heat, you know, from the electric field there. So it's best to brush as best you can. Even after I brush often enough, I have to go back and touch up with some kind of solvent to get some of that off. And xylene or acetone or something pretty strong will usually take that residue away. And then of course you need to clean out holes with either a brass hole brush or with pegwood or toothpicks or whatever form of that sort of thing that you like to use in the shop for cleaning out holes. And of course the rotor and field get set aside. They don't get dunked. There's nothing you need to do. Maybe blow the dirt off with a compressor, and that's about it. It's a good idea to clean and re-lacquer the bezel and hands if you want to be that particular. It makes a big difference in the appearance. And you want to clean the glass and hand clean the dial at most with diluted dishwashing soap and water. Nothing stronger ever. Those dials, that paint on those dials has been baked over the years. It's aged, it's been heated. It does not like to be aggravated with any kind of solvent or anything more than dishwashing soap on a clean rag or towel, and just wipe it down. And that's as much as you should ever have to do with those. And if it doesn't respond to that, it's probably not going to respond well to anything else. So that's probably as good as you can do. So here's our failure points in this clock. The rack, roller and pawls are failure points I show here. The roller, what gets you there is the rivet that holds that roller in place often wears out so severely that that roller just flops around. And then this pawl right here above the roller is another failure point. We'll show you more detailed pictures. And of course, the long bearings on these wheels tend to get caked up with dirt. They have to be cleaned very well. Sometimes they wear. Honestly, it's more often easier to change the arbors than it is to try to rebush these, because there's often not enough material to work with as far as rebushing is concerned. Sometimes there is. You just have to use your judgment when you delve into it. But usually they're not, on this clock, they're not terribly worn. I think one of these I decided to do a new arbor for, you'll see later. The other one was fine. So here we go. Here's the strike wheel ratchet, and you can see this wheel, as best as I can figure, is supposed to be a 1/2 inch in diameter. And this one is 0.475, and it is so worn, and you can even see it there. The ratchet, the little ratchet clicks don't even come in contact with the wheel, and that's not going to work. So there has to be continuous engagement there for this to work. And there's nothing here in this picture at 475, doesn't even touch. So, and I know that if you go to a 1/2 inch, you have much better results. Now, of course, this wheel also had other problems. These clicks just wobbled around back and forth as loose as could be. So that had to be dealt with too. They were both worn out and loose. So that pretty much is what needs to be done there. Also, wear on the arbor and the center hole too can be experienced from time to time, and those can also be addressed with typical clockmaking methodologies. The rack with these 2 pawls you can see here, actually this wear is not as bad as I've seen it. I've seen these things wear deep grooves, and once they do, you lose travel on that ratchet, which drives the entire strike sequence, and you can't get the proper strike sequence anymore. And then you have to replace that little pawl, and it can be done. And again, the rivet also wears. So let's delve into getting after this ratchet for starters here. And you can see what we're doing here is I made up a little ring. It's 228 ID, 1/2 inch OD, and about 156 inches thick, and dropped it over this entire assembly, and then use a pair of pry bars to pull off that. This is a bushing that's pressed on, and it's meant to retain that ratchet wheel and pinion assembly, and it's easily removed as I show here. And then you've got your little ratchet wheel free. And of course, I get a little reverse here. I didn't clean first before I took this apart, but subsequently it's shown in clean form because it went into the solution right after this and got cleaned up. So here we go. We're going to make a new ratchet for this thing. We're going to use an unusual method, but it works very well. We start out with a 1/2 inch stock, center it up in the 4-jaw. This is a 4-jaw chuck spinning here, and it's been centered up. So this is running true. Then we run a 1/4 inch hole through it, and then we get it on the mill and cut the ratchet. I have a little bit more detail in the references at the end of the presentation for the geometry of that cutter, but chances are there's an off-the-shelf cutter that'll do it, or you can make one up out of a mill cutting bit pretty quickly with a grinding wheel. And there's 19 teeth on it, and very quick to make. Doesn't take long to make 19 teeth on a ratchet. It comes together pretty quickly for you. I usually like to leave maybe a 10 to 15 thousandths inch uncut area, just a little edge there on the tooth tip. I don't like to have sharp tooth tips because I think that invites damage. And so just maybe a 10 to 15 thousandths reveal on those tooth tips, and you've got it. And you can see on the right here what you're left with. I bore out that, originally cut it to 1/4 inch, and I bored out the 335, parted off at 70 thousandths thickness, and we're ready for the next step. So next, what we're going to do on the left, you can see it, is we take the old ratchet slash pinion assembly. We set it up in the shoreline with the collet attachment, and we use the drill that's shown here just to get it to run true. I could actually have taken that out of there to do the machining, but I had left it in. I found a drill that was a tight fit to that hole and used that to help make sure that part was sitting in that chuck running true. It's very important that it runs true when you do this cut. So then what we do is we trim away. First, we get rid of the teeth and trim away until the inside of that ratchet that we just made and cut the 335 just fits. And I mean just fits is you need to apply a very slight amount of pressure to get it to go on. And I don't mean that you have to hammer it on. I mean, you can get it on with your fingers, but you got to be just a little bit of force to get it on there. And it's good and snug. Then what we do is I found this. It was an old stump from an old bushing tool that I had once. I don't know why I still have the stump, but I found the stump. And it turns out it's a really great tool for this, because what you do is you'll smear an extremely thin layer of oil on the top of that stump. And then you'll lay this assembly here. You remember we said we pressed the pinion ring, or the ratchet ring onto this trimmed wheel here. And that's the result. And I just place a little bit of flux. You can see the no corrode paste flux there. And we cut 3 small segments of solder off of our 18 gauge solder, rosin core solder, standard lead tin eutectic solder. And we place these 3 little segments right there. And then we heat up the stump, not the part ever, just the stump. And you'll be warming it, and eventually you'll see that solder just take off around that edge and flow in. And you can see here on the right the result of that. And we just clean off the excess solder, and we clean off the excess flux. And that's what we've got. So the reassembling is pretty straightforward. We obviously at times have to rebush the center hole. So we clean all the flux away, rebush the center hole. And then in this case, I made new rivets for the clicks because they were bad. They were just worn way out. And I have a reference at the back for the dimensions of those rivets in case you need to look at that. And then we test the function of it and make sure that the click operates as it should. And it grabs when you try to turn it in the wrong direction and allows free movement in the other. And we reinstall the retaining hub, and we polish the pivots on this part, and it's ready to go. And we've probably are about 60% of the way through restoring this clock now, because that's a big part of it. That's a big part of making these things work right. Okay, so I'm going to jump over here into the next part. Oh, we're all the way at the end. Let's dial up to the top. Start part 2. So now we're going to get after these pawls in this rack. Well, if you have wear in here, the problem is that generally, so you got one side of this pawl works on the cam that gets lifted every half hour to strike. The other side just bumps up against the snail. So obviously the side that's getting most of the contact is going to be the one that wears the fastest. And that's not what we want to happen, because as that wears, it creates a situation where it sets the rack right before it drops off at the wrong height. And the wrong height means it's not going to drive the strike wheel as far as it needs to go in order to be able to count down all the counts. So this could be a real problem. And when you get these things in and they don't strike right, the first thing you do is you look at this thing and say, okay, where are we with it? And do we have enough travel so that we can complete the strike sequence? And usually you don't. And so you want to replace that part. But what we're going to do is we're going to actually make the critical dimension of this part 10 thousandths more oversized than maybe we would otherwise. And the reason is because guess what happens? The cam wears. The part that the ball runs, or not ball, but roller runs across, that doesn't wear. But the part that the actual pawl, this runs across, this against that cam creates wear. And now you got a problem. So you got to deal with that wear. And so the way we're going to deal with the wear of the cam, I don't want to make a new cam. I really don't. It's a complicated part. It's steel. It's going to take a lot of effort, and it's super precise. And it's just not something that we want to do. But we can make up for it by making this part a little bit bigger. So here's how we get this out. We mount up this rack in the vise. And what we do is we take a piece of 1/4 inch brass rod and we saw a groove in it. In this case, I just used a bandsaw and followed up with a file until it was just wide enough to clear the side of that rack. And then you go at that with a hammer and a couple of taps, and that part drops right out. Now it's held in place by over here. If you look at where the pawl was, there's metal here extended into that area and bent down at manufacture to hold that in place. But guess what? that metal gets pushed out of the way, and sometimes it gets broken off, and it really doesn't make a whole lot of difference, because when we make this part, it's going to be so tight in there, it's not going to want to come out. And if you are worried about it, you could always put a very small dab of solder or something right there at that edge and just get it to flow in to hold it. But I've never had to do that because these things hold so tight in there. You have to pound them in with with a tool to get them in the first place. They just don't want to come out. So that's relatively inconsequential if something happens to that crimp. So here's our pawl. Here's the dimensions. They tend to be fairly close. Here's the blank size. It's made from 01 precision ground tool steel. You can buy this stuff from practically anywhere. It's 3/64 standard stock size. We need to grind that down to 44, 43 to 44. And that's not very difficult to take through, 4 mils off of the thickness of this tiny part once it's made. I use the, I use either a combination of the work sharp with a, let's see, what am I using now? I believe it's a 220 grit on that thing, or even a 400 if you're patient will do it. But the important thing is that this dimension right here between the faces and the groove has to be 150. Remember, we said it's originally 140, and we cut, and both, by the way, doing these two clocks, I compared them. They were both the same. So no kidding. These were originally 140. We're going to make it 150 because we want to account for that cam wear. And it's about a 20-minute operation to make this part from start to finish. You can cut out the raw metal with a hacksaw if you want to, and then just sand the edges smooth and clean. This little round quarter moon here in the middle between the two faces was originally meant as part of that crimp operation I showed earlier. And if the two sides of that crimp are broken off, you probably don't have to worry about putting that half moon in there. But there's usually enough left of at least one side to get use out of it. So I do continue to put that little crescent in there. This little cutout here in the back, this groove, you can basically, what I've been doing is just using a jeweler's saw to make a single kerf through there, and then filing up with a file and following up with a file there, and that you probably have a file in your set of tools that'll get in there. It's relatively broad and pretty easy to file through. And of course, as you would expect, there's a pretty sharp angle on this part. So we bent that in the vise by crimping it in the vise and then tapping on it with a brass block until it was bent to the right angle. Not difficult. Takes a few minutes, but it's all very doable. And so here we are. We take the same tool that we pushed it out with, and we use that tool to drive it back in, and you can see it there. We want to put a nice, clean, round edge on that face before we drive it in. So polish that up with some 1000 or even 2000 paper to get a nice smooth surface, so it doesn't go and start creating more wear on that probably somewhat worn out cam. Okay, another little tip that's very important is this is the bearing on which the rack runs. In other words, so you can see the spring associated with that rack that drives it here. This is the rack arbor, and this is the hole and pivot that it operates on. If that wears out, and it's steel on steel, so you get some pretty ugly things happen sometimes. If that wears out, it causes interferences over here between the rack itself and the pinion it's driving. And it can be so excessive that it'll seize up the strike and it won't do anything when it comes to strike. And I've had this happen a couple times, and the solution is to file the hole back. And even if you go over a little bit in the other direction, it's not going to hurt anything. They really they have these things overly, the depth of these is too heavy. And they do that on purpose to increase the surface area between those two, because otherwise you might end up wearing through that pinion pretty quick. But I think they overdid it in the design of this thing. So if you file this hole back to where it should be and go a little further, it's probably okay. And by a little further, I mean 10 thousandths, 15 thousandths is probably fine, it'll give you a little bit of clearance there. You have to be able to see light between the tip of that pinion leaf and the valley of the groove in the rack teeth. You have to be able to see light there. If you can't see light there, you're going to have an interference, and it's going to bind up and it won't strike at all. So something to consider. You can see the little brass bush that was put in there. That one was pretty worn. This one was fairly worn on this clock, which is not surprising. So then there's the post, and these are the posts upon which ride the various idler wheels. And these are real easy to clean up. You just hold this plate in, there's posts on the other side. You can hold those posts in the vise, and just, this is a strip of 1000 paper cut thin, and just use like a belt to run back and forth on that post in various directions until you get the whole thing covered. It takes no time. And if you follow up with a strip of 2500, you have a beautiful smooth surface, and that's about all you have to do. Now on this particular clock, this post, and again, I had two clocks. One clock was fine. All the posts were fine. This one was terribly worn. The oil must have dried up. It must have become like varnish, as it tends to, and then the thing just wore itself out. The hole was a little large on the pinion that rides on that, but making the post just slightly larger in OD took care of that. So there was no need to do anything else once that was turned up, and you see the part here ready to be separated here from the 12014 quarter inch steel stock that it was made from. And 12L14 is fine. It's plenty adequate for this. There's not a lot of force on these parts. They can wear out, but if you keep these clocks lubricated, they probably would last nearly forever. It's just that they never get lubrication because people really don't know to lubricate them. So. All right, so now let's reassemble. We start with the seconds, this little seconds bridge here with the two screws. Don't forget to put the second arbor in there first, or you're going to have a problem later on. And then we put the two idler wheels back in, and then we press the washers back on and just slightly peen that arbor. Once we do that, you could put a block underneath where it protrudes in the bottom of the plate, and just slightly peen that arbor. Very so slight is all you need. You don't have to pound the heck out of it. You just a couple of light taps, and that washer's not coming off, and those wheels are secure. And then here's our number 42 drill that we're going to use to align up these cams, and it takes a little fiddling around to get everything lined up, but once you do, you're done. So it's worth the trouble. And there you see it all set. And once you get this set up and you pull that drill out of there, you don't have to worry about it. It's not going anywhere. Nothing's going to move. And after that, if it shifts or a wheel turns a little bit and it moves, it doesn't matter because things are already in alignment. So we're in good shape. Then we want to put our wheel back on, which also has the hour snail, and you can see it there. I show a view of the upside down version of that. This wheel, you can't even, the one of the crazy things is, one of the good things about having this alignment set up with this drill is that you can't even see this snail when this movement's assembled. You literally, it cannot be seen. So taking care of this by getting the alignment in place now is a really good plan. And so here you see now I've also installed the rack. I've installed the strike hammer and the strike wheel, and there's a little spring here we're going to talk about in a second. It's very, very important. Then we want to install the front plate and align everything up and tighten down the screws. And I'll tell you, this has got to be one of the easiest clocks to assemble. I mean, once you got all the parts in place, it's just minutes to have this thing back together again. Then we flip it upside down. We put the field assembly on. We put the rotor on, the bell, and the hammer, and we're in business. So here's a couple of tips with respect to these springs we just talked about. The strike spring needs to be rehooked and reloaded, and that's easy. You just push it over the top of this little retainer tab that they've built into it. On the left here, we have a very important spring. This little spring, be careful because you'll lose these if you don't watch what you're doing. This spring will take off on you and it'll be gone. But if you lose it, it's not hard to make a new one. It's 10 thousandths thick piano wire, bent up as I show it here. If you're looking at this this wire, it comes across, it comes towards you, it goes down and then to the left, and it's symmetrical on both sides. And you can see why. One side has to hook to the plate, the other side has to hook to this the strike pawl. And what you'll notice when this is set up is this lever over here that's bent up towards the strike wheel is going to be suspended right there in the middle in between its two extremes. And if you push on it, it'll, in either direction, it returns right back to where it is. And it acts as a little mini ratchet when the strike mechanism winds so that the strike wheel can go in the other direction without any harm and without jamming up against anything. And then it's ready to go when the strike wheel starts to turn and needs to lift the hammer. So real easy part to lose though. So kind of keep an eye on it when you're disassembling and cleaning. I had one in one of the clocks that I did this time around. One was just plain missing. And if it's missing, nothing happens. It doesn't strike it. It doesn't do anything. So it's a big problem losing it. Okay, so now remember we talked about the strike wheel home detent. Well, here it is. You see the little crescent half moon there on the left in that little window. There's an observation window cut in the front plate of the clock, and you just look through there and you can see that little half moon. If that half moon isn't where I show you right here, when that rack is ready to drop off the cam, this thing is not going to strike right. And it can be just a little bit off and it won't strike right. So it's real critical that that be placed right there. And about the right location seems to be just a little bit below the strike pawl, the arm of the strike pawl, the little tab of the strike pawl that's bent up. Just a little bit below it seems to be the right place for it. And every clock I've done seems to behave very well as long as you hit that spot. So how do you get it there? That's the question. Well, what you do is you turn the time set until your cam has pushed your rack all the way up to the top and it's ready to drop off for the strike. And when we're probably about, I'd say if I had to guess, 2 minutes before drop off, at that point, what you do is you push that rack out of the way so you can move this pinion. It doesn't take much to move it. It bounces back when you're done. You're not damaging anything. And you just turn that, you rotate that pinion and that entire strike wheel until you can see that detent in the window. And there it is. You release the rack and let it re-engage with the pinion and lock it in place. Now, I'm going to tell you, about half the time you do this, you're not going to be able to get it to where it is. You're going to either have it at aligned too far up, or you'll move it to the next tooth and it'll be too far down, or even further up. Well, when you get to that point and you finally have it about as close as you can get it to that location, and you can't get it to that last little bit, well, there's one more thing left that you can do. And that's this is what it is. If you look at this picture, you'll see that I put a wrench, a 1/4 inch wrench, open end wrench on that strike wheel arbor. It's a hex. Now, that's not a coincidence that it happens to be a hex. That was done there that way on purpose by Telechron to make that wheel adjustable. It turns out that the joint between the pinion / arbor, where it intersects that wheel with the teeth on it that drives the strike, there's a little bit of a clutch there. And I won't call it, I should be careful in calling it a clutch, because a clutch would kind of imply that you can move it at will, and you can't. It's a lot like a hand bushing, a friction tight hand bushing on a clock, where you can move it a little, but if you start using it to rotate things around all over the place, you're going to wear it out and you're not going to have a clutch anymore. So this is for very fine adjustments only. This is the last step. When you're moving it, maybe a 16th of a 32nd of a turn or some small amount like that, just maybe 50 to 100 thousandths, you're nudging it. And I mean nudging it to get it to where you want it. And what you do is you hold on to the tooth strike wheel with your finger, or if you're careful, with a tool, and you just nudge that arbor with that wrench to get it where you want it. So it's a fine adjustment for that arbor. Took me forever to figure this out. And it makes a big difference knowing that's there in terms of getting this thing in its final adjustment so that you can get it to strike right. So some final thoughts. This methodology that I just showed is deterministic. If you do it this way, 100% of the time, these ship's bells will strike properly. If you skip the steps, I don't know. Maybe it'll work, maybe it won't. Most of the time, if it doesn't work, what'll happen is you'll miss half-hour counts. You'll get other erratic results. I mean, people report that the strike sequences are reversed. Funny things like that. If you're not careful with the rack, the pivot we talked about on the rack, you'll have interference between the rack and pinion, and that's a problem. So you got to take care of that as well. And when it jams, it jams. You cannot get it to strike at all. So that's a real important one. So those are the biggies. And these adjustments have to be made just this way. And the good news is there's only one real fine adjustment on this thing, and that's getting that strike wheel in the right alignment. And that's pretty much it. And if you could just use this presentation in its pictorial value, you'll be able to, go to the bench and make these adjustments, and you'll get a good result. So as a reference, this is the ship's bell sequence, and it's really simple. I mean, on 4, 8, and 12, you get 4 double bells. And at the 30s, at 4:30, 8:30, and 12:30, you get a single bell. And so then when you advance an hour, 5, 9, and 1 o'clock, you get 2 bells, and then an additional one at each half hour, and on it goes all the way down. So it's a fairly straightforward thing to understand. If you think of it in terms of 1, 2, 3, and 4, and then it just repeats at 5, 6, 7, 8, and again at 9, 10, 11, and 12, it's pretty easy to keep it in mind as you're going through and testing to make sure your ship's bell is working properly. Here is the reference for the click rivet if you want to replicate it. The dimensions there are pretty much the most critical ones, the 0.62. The other ones you could do kind of by eye if you want to, or per fit. And then the 40 is based upon the wheel thickness of 32 at about 8 thousandths to rivet. And then the ratchet pitch, if you're trying to make or buy or find a tool for to cut the ratchet, the angle that seems to work the best is about 60 to 65. And if you align the original wheel to this surface, you get exactly the right pitch that you need to make this wheel work properly. You can't use this other surface, the original, if you will, friction surface, because it's usually beat up, deformed, worn out, gone. It's just not useful. But this reference here, this surface, if you align when you set up the cutter, if you align this surface to the original wheel, you get very, very good results. Some interesting references. Here's the replacement rotor reference. Dave Friendland's the guy that does this work on these rotors, and he's really good. He does a really good job. I do rotor restorations regularly, but I don't like to do them just as rotor restorations because it just clogs up my workload and I just don't have time to do other things. But Dave does a really, really good job. The rotor in this clock is unusual. It's not a B rotor, it's a BF rotor. It has a short neck, 18-tooth pinion, and he advertises that he has these things or that he'll rebuild yours. And here's the Jim Lynn's reference on electrifying time. And a really interesting site to visit if you're interested in Telechron clocks is telechron.net. And I think his name is Pappy. I think he's got every Telechron clock ever manufactured on that site in pictorial form if you need a reference. I have yet to not find something on that site that I was looking for. So, and that's what we've got for today. Happy to take any questions that anyone might have.
Yeah, Ken, thanks. One question has come across the chatter. How much do you charge for this kind of repair, and is it efficient?
I find that it's relatively efficient. I can, if I got multiple clocks in, I can batch up the various steps You know, if you're making one ratchet, you can make two ratchets. It's not a lot of work. If you're making one pawl, you can make two. You know, you just continue to cut further and slice it, you know, that kind of thing. So, I mean, I can get efficient on these things. The thing is that if you do one at a time, it's going to be a little slow. If you've never done one before, it's going to take you a little while to get used to this. I'm going to tell you, I mean, these don't work like normal striking clocks. So you're just going to have to look at it and say, okay, I'm going to have to learn how this thing works because it's not similar. I can actually, on a clock like this, I can actually charge on the order of $300, and it doesn't, I mean, and that includes cleaning up the case.
Oh,
So, you know, it's not terribly bad. I mean, depending up, and of course I say that, but that depends upon what kinds of things have gone wrong. You know, so if you have to make a ratchet wheel, that's one form of that's one cost basis. If you have to replace a pawl and everything else in the clock is in good shape, maybe a bushing or two, that's another cost basis. If you have to rebuild the rotor, and you know, by the way, that includes the rotor restoration, that's, you know, you're never gonna, I'm gonna tell you this, you're never gonna do one of these clocks and not have to do something with the rotor because they're all worn out. Now, the good news is that these are less worn out. The Telechron ship's bell wears out rotors a lot less than the standard striking Telechron electric clocks do. So the wear you're going to deal with is a lot less than it is in some of the other ones. And usually what happens with the rotors is most of the wear that you end up having to get after is because the lubrication dried out and the things turned into sludge, and the poor thing has to drive its own sludge. And that wears it out more than running the clock. So if you can get at the rotors and get at these clocks before the oil has failed, I mean, you're way, way better off. And, you know, by the way, I mean, if the oil fails within the movement, the rotor is going to wear out in great excess as well. So again, if these things are kept lubricated, I mean, it's better for everything, but often they're not. And when you get them in, you just have to deal with all the issues.
Ken, the 19 tooth ratchet that you made,
Yes.
you have a digital divider that's a little pricey for most homes, most shops.
Well, you have to remember that this is a ratchet. And if you take an Excel spreadsheet and you just divide 360 by 19 and have it basically, you know, start with 0 and add that amount until you go all the way around the 360, you can create a table. And then you can actually use the simple, Shoreline makes a rotary table that is calibrated in fractions of a degree. And you can use that to do this. And that device is not anywhere near as expensive as the CNC rotary table that I use. And you can get good results with that. And just have to be careful, because if you calculate wrong or you turn it wrong, you're going to end up with a little bit of a problem there. But I mean, again, as I said, it's a ratchet, which means if you're off by, a little bit, you're probably not going to realize any problem with it in particular in this clock. But, you know, obviously you don't want to be off by, you know, a couple of degrees or anything like that, but a small fraction of a degree just due to rounding error as you calculate the values on a ratchet, you're probably okay.
So with the standard Shoreline rotating table, you could do that.
Yes, you could do, without a doubt. And I used to make ratchets this way with that for a long time until I finally, I mean, 19 divisions is not that difficult to work with. When you're dealing with a wheel that's got 60 or 80 teeth on it, you'll drive yourself crazy with an Excel spreadsheet and trying to dial in all those values. But on a 19 tooth ratchet wheel, it's nowhere near as difficult.
Yeah, 19 squared is 361.
Yeah, well, it's getting pretty close. Yeah, what is that? Let's see. It's just under a nice round value. I'm just pulling up a calculator here. 360. Yeah, 18.94 degrees per setting. So, you know, I would just take 18.94 and multiply it by 1, 2, 3, 4, 5, 6, 7, all the way down until you get to 19, and so that you have a table of values. Well, actually, this is 18.9473. Yeah, anyway, you get the point. You can do the math with Excel, and you don't have to do any thinking, and then you can figure it out from there when you use that. It's very doable.
Yeah,
Hey, Ken.
thanks.
Absolutely.
Hey, Ken, were you, the ratchet, you soldered it onto a hub,
Yeah.
I'll call it, obviously a very strong fit. Could you, if you had a good friction fit, could you have used like a thin wicking CA or a retaining compound instead of soldering? Does that, either of those work with brass, or is there too much force?
I don't know. I've never done that. I wouldn't use CA. If I was going to do anything, I'd use an anaerobic.
Right,
But a CA, I don't like CAs for this sort of thing because they act funny under pressure and heat. They'll dry on you in the worst possible time, and then they're stuck having to dissolve it out. But an anaerobic gives you a little bit of working time. It might work as long as it's a tight fit to start with. But I mean, to your point, it's not that much force on these. I mean, you got to figure, when you actually play with this thing and actually play, you feel how much force that rack is bearing down on it. It's not a huge amount. It's not like, I would never do this, by the way, in a clock where I was replacing, a mainspring driven clock where I was replacing a ratchet. You just cannot do that. You cannot solder it. But, I say that, but on the other hand, many of the barrels that you work with in spring wound clocks, those barrels are soldered to a base plate, to the wheel itself. I mean, you get in there and you look, now it is usually done in a way where there's a tongue and groove, but it's soldered. But it's soldered. The key though, to a good solder joint is surface area. If you have poor surface area, you're not going to get any kind of a strength in the joint. But if you can get, like on this wheel, you get a fair amount of surface area because you're going all the way around the wheel and you had a fairly broad amount of geometry there. So it solders and holds extremely well.
yep, understood.
And I'm not big on soldering. I really avoid soldering, but in some cases, it's just the only way to go. So,
Right, I know that you're not a big soldering fan. That's why I asked about the retaining compound, if that would work.
yeah. I mean, in many clocks, there were solder joints used, but they were so well hidden that often you don't even know they're there. If you look at older English clocks and even some French and German clocks, many of the arbors are soldered to the hubs that hold the wheels, but you'd never know it until you try to drive it off and you go, uh-oh, there's more here than friction.
Thanks.
But yeah, I don't like this, but this is one where, I mean, the only other option is to remove that pinion and to drive the wheel direct back into have the wheel, have a smaller ID and then drive the pinion back into it and stake it. The problem is with this one, it's not brass, it's bronze. The pinion is bronze, and that bronze is hard and it's brittle. You try to drive it off and it just cracks. So it's not a good thing. And so that's really is not a workable way to do it. And so this method seems to come in and save us. And we used to use this back in the early days. We would use this method to do escape wheels because there's very little force on an escape wheel. And if you created a ring that was basically your new teeth, and you cut your original wheel, you cut the teeth away and got that to fit tight, then you could solder it and sand it out or turn it out, and you wouldn't even know that joint was there. But I kind of stopped doing that because it actually, when I started making these wheels, I started realizing that the toughest thing was making the blanks, and I can get away from having to make the blanks by having the blanks cut outside, and that's kind of what I went with for a lot of this stuff. And in cases where I don't have blanks, I just said, the heck, but I'm not going to do the crossing out. We'll just forget the crossing out because it doesn't bias anything. I mean, it's cosmetic. And if it's visible, yeah, then we'll cross it out. But if it's not going to worry about it. And it's a lot less time than doing that ring thing and soldering it. So it takes less time, and it's a more solid solution. Dick, your fall background is gorgeous.
It's springtime.
It isn't spring. It looks like fall. It's beautiful either way. Anybody else have any other questions?
I have a question. If you've ever thought about making a Zoom meeting on the rectangular sessions, Westminster electric clock movement. I think CJ Hug was the guy that had a session's name on the dial. Are you familiar?
I think I know what you're talking about. Is that the one that resembles the 2-train Westminster sessions?
It's rectangular, and then the motor bolts on the back of it where the gear goes into another gear in the, I got one in my hand here.
Oh, you should show it to us.
Well, I'm not sure I know how to navigate. I lost my big picture here. It says Zoom in the middle of my blue. Yeah. How do I get it back on so you can see me?
Well, you'd always, if you wanted to, you could always send me a
Picture of it, okay.
and with a picture, and I'll take a look at it for you.
Yeah, it's probably 4 inches long and maybe 2 inches tall. And then the hammers are, there's 4 hammers on the end of it. That move, it's kind of complicated.
Interesting. No, I'd love to see it and try to.
Yeah.
I probably have seen it, but it's not
Yeah.
ringing a bell. You could probably describe one of the slides in this presentation I just did, and I wouldn't know what it was you were talking about without the picture of it. So yeah, sometimes a picture's worth 1,000 words.
Yeah, there's a patent number on the back of it too, manufacturing patent number, but I've got maybe 3 or 4 of them. I don't. They use one similar in a little miniature grandmother, maybe it's about 2 foot tall or so, a little like a small grandfather clock where the chimes hung vertical. Where the first one I seen was in a mantle clock and it had the chime rods at the bottom, but the dial had a sessions dial on it.
Yeah, go ahead and send a picture. We'll take a look and see what you got.
Okay, I'll do that. Yeah,
Yeah, for sure.
thank you.
Sure. Anybody else? Gonna go out and buy one of those. They're not that easy to find, actually. These Gloucester Yachtsmans, Resolutes, and Nantuckets. There's not many of them out there. I've noticed on eBay. And when they show up, oh my goodness, they are super expensive. I've seen some of them go for $300 or $400. So when they quote unquote work, which I always question that, but still, it's surprising to me how few of them seem to be available for sale out there in comparison to other Telechron electric clocks, where there are literally floods of them out there. All right. Well, I guess that will conclude things then. And of course, as always, if you have other questions, you're welcome to shoot me an email, and I'm happy to take the time with you to help you figure whatever it is out. If you get stuck on one of these things, you can always check in with me, or we'll have the presentation up for viewing in a matter of a few days here for those who are interested in pursuing that. So, okay, again, I want to thank everyone for attending tonight. It's really great to have a strong audience of interested folks following along here. And I guess we will see you next time. So,
Thanks, Ken.
Well, thank you very much for your presentation. It was very informative.
oh, thank you for your
It
attendance.
was really interesting.
Yeah, thank you.
Thanks a lot.
Okay.
Thanks, Ken.
Thanks, Ken.
Thanks, Ken.
Okay. Take care, folks. Thank you.
Thank you, Ken.
Thank you, Ken.